1.5 Exponential Functions. The outline of this video is as follows. We will discuss the fundamental definition of exponential functions and explore their unique behavior, where a quantity changes at a rate proportional to its current size. From there, I will introduce the special and powerful natural exponential function, which uses the number e as its base, and explain why it is so essential in mathematics. We will then apply these ideas to build models for both exponential growth and exponential decay, seeing how a simple constant can determine whether a quantity increases rapidly or diminishes over time. To make this all concrete, I will finish by walking through several key applications, including how we calculate the growth of a financial investment and how scientists use radioactive decay to determine the age of ancient artifacts. This will provide a complete picture from theory to practice. Let us begin by defining what an exponential function is, as it is a crucial tool for modeling rapid change. An exponential function has the general form f of x equals a to the power of x. In this form, the letter a is called the base, which is a positive constant that is not equal to 1. The most important feature is that the variable, x, is located in the exponent. It is essential not to confuse this with a power function, such as f of x equals x squared, where the variable is in the base. This structural difference is what allows exponential functions to model processes that involve extremely fast change. For example, population growth, radioactive decay, or how an investment grows with compound interest. The key takeaway is that for exponential functions, the variable is always in the exponent. Let us explore what happens when a quantity grows by a constant factor, a pattern that is the foundation for an important family of functions. Imagine we start with a positive quantity p. If we double it, we have 2 times p. If we double it again, we get 2 times the quantity 2p, which simplifies to 2 squared times p. A third doubling gives us 2 cubed times p. This process shows how the number of doublings, our variable x, appears in the exponent, leading to the function f of x equals 2 to the power of x. This is called an exponential function because the variable is in the exponent. Be careful not to confuse this with a power function like x squared, where the variable is in the base. The main idea to remember is that exponential functions describe any quantity that changes by a constant multiplicative factor over equal intervals. Let us see how annual compound interest provides a perfect real-world example of an exponential function. We begin with an initial deposit, called the principal. After 1 year, the account earns interest, so the new amount is the original principal p times the quantity 1 plus the interest rate r. In the second year, the key is that interest is calculated on this new, larger amount, not just the original principal. So, we multiply the first year's total by the quantity 1 plus r again, which gives us p times the quantity 1 plus r squared. This pattern continues, and after x years, the total amount a is the principal times the quantity 1 plus r, all raised to the power of x. For our example with a $100 principal and a 5.5% interest rate, the formula is 100 times 1.055 to the power of x. This is an exponential function because our variable, the number of years x, is in the exponent. Now let us see what our investment formula, a of x equals 100 times the quantity 1.055 to the power of x, reveals about the nature of this growth. This table shows the account balance and the dollar increase for the first 4 years. Notice that the growth is not constant. In the first year, the account increases by $5.50. The next year, the increase is $5.80, and it continues to get larger after that. This happens because each year we are earning interest on a slightly larger principal amount, which includes the interest from all previous years. This pattern of accelerating increases is the hallmark of exponential growth, so do not confuse it with linear growth, where the increase would be the same fixed amount every period. The key insight here is that with exponential growth, the amount of increase grows right along with the total value. Let us begin by reviewing what exponents mean when they are integers or fractions, as these are the building blocks for all exponential functions. If the exponent is a positive integer, like n, then a to the power of n simply means multiplying the base a by itself n times. By definition, any non-zero number raised to the power of 0 is equal to 1. A negative integer exponent, like negative n, indicates an inverse, meaning it is equal to 1 divided by a to the power of n. Finally, a rational exponent, like the fraction p over q, represents both a power and a root. For example, 8 to the power of 2/3 means we first take the cube root of 8, which is 2, and then square that result to get 4. Notice you can take the root first, which often makes the calculation much simpler. These fundamental rules allow us to evaluate expressions for any integer or rational exponent. To make sense of an exponential function for all real numbers, I need a clear way to handle irrational exponents, which we define using a process of approximation. For an input like the square root of 3, we can take a sequence of rational numbers that get closer and closer to its true value, such as 1.7, then 1.73, and so on. If my function is 2 to the power of x, I can then look at the sequence of outputs: 2 to the power of 1.7, 2 to the power of 1.73, and so forth. As the exponents get closer to the square root of 3, these output values converge to a single, unique number. We formally define this limiting number to be the value of 2 to the power of the square root of 3. This method ensures that the graph of an exponential function is a smooth, continuous curve with no gaps or jumps. The visual shape of an exponential function, y equals a to the power of x, is determined entirely by its base, a. When the base a is greater than 1, the function shows exponential growth, meaning its graph starts low and rises increasingly steeply as you move to the right. For instance, the graph for a base of 4 climbs much faster than for a base of 2. Conversely, if the base a is between 0 and 1, the function shows exponential decay. In this case, the graph starts high and falls rapidly, approaching the x-axis. Despite these opposite behaviors, all of these graphs share one crucial feature. They all pass through the point 0, 1, because any positive number raised to the power of 0 equals 1. Therefore, the base tells you whether the graph rises or falls, but the starting value on the y-axis is always the same. To work with exponential functions effectively, we rely on 5 fundamental properties that simplify expressions involving exponents. The first 2 rules address multiplication and division when the base is the same. When you multiply 2 such terms, like a to the power x times a to the power y, you add the exponents, and when you divide, you subtract them. The third rule states that raising an exponential term to another power, as in the quantity a to the power x, all raised to the power y, is equivalent to multiplying the exponents. For example, 10 squared raised to the third power is just 10 to the power of 6. The final 2 rules show how an exponent distributes over a product or a quotient within parentheses. These properties are the essential toolkit for manipulating any exponential expression you will encounter. Let us see how these rules for exponents work in practice to simplify expressions that might otherwise look difficult. For instance, if we multiply 3 to the power of 1.1 by 3 to the power of 0.7, the common base means we can just add the exponents, resulting in 3 to the power of 1.8. Or consider the quantity 5 raised to the square root of 2, which is then all raised to the power of the square root of 2. Here, we multiply the exponents, and since the square root of 2 times itself is 2, the expression simplifies neatly to 5 squared, or 25. The rules also apply when the bases are different, but the exponents are the same, such as 7 to the power of pi times 8 to the power of pi, which becomes the quantity 7 times 8, or 56, all to the power of pi. The key idea is that these rules allow us to systematically simplify expressions involving any real number exponents. The single most important base for an exponential function is a special irrational number we denote with the letter e. This number is approximately 2.718, and much like pi, its decimal value continues forever without any repeating pattern. It might seem strange to use such a specific, non-integer base rather than something simple like 2 or 10. However, the unique properties of e make it the ideal choice because it significantly simplifies many essential calculations you will encounter in calculus. The function f of x equals e to the power of x is so fundamental that we call it the natural exponential function. Remember that this function, built on the special base e, is the cornerstone for modeling many processes in science and finance. Let us explore what makes the number e so fundamental in calculus, which all comes down to the steepness of an exponential graph. As the base a in the function y equals a to the power of x gets larger, the graph becomes steeper where it crosses the y-axis at the point 0, 1. For example, if we look at the graph of y equals 2 to the power of x, its slope at that point is less than 1, at about 0.7. If we increase the base to 3, for the graph y equals 3 to the power of x, the slope becomes greater than 1, at about 1.1. The number e is the unique base that sits between 2 and 3, producing a slope of exactly 1 at the intercept. This special property is why e to the power of x is called the natural exponential function and is the most important base we use in calculus. We can now generalize the exponential function to model many real-world processes involving growth or decay. This powerful model is written as y equals y naught times e to the power of kx. Here, the term y naught represents the initial amount of a quantity at time 0. The most critical part of the model is the constant tech, which determines the rate of change. If k is a positive number, the function describes exponential growth, where the quantity increases at an ever faster rate. If k is negative, the function describes exponential decay, where the quantity shrinks over time, approaching 0. For instance, an investment earning continuous interest follows a growth curve, while the amount of a radioactive substance like carbon-14 follows a decay curve. Therefore, the sign of the constant sock is the key piece of information that tells you whether you are modeling a growth or a decay process. Let us now consider a different method called continuous compounding, which is a powerful model for investments where interest is applied constantly. For this, we use the formula y of t equals p times e to the power of r times t, where the letter e is a special mathematical constant. Using our same scenario, the initial principal p is $100, and the rate r is 0.055. To find the amount in the account after 4 years, we calculate I of 4, which is 100 times e, raised to the power of the quantity 0.05, 5 times 4. This gives us a final value of approximately $124.61. Notice this is slightly more than the amount we found with annual compounding, and that small increase is the result of the interest being added in at every moment. The key idea is that continuous compounding uses the base e and will always yield a slightly higher return than compounding over discrete time periods. Now we can see a powerful application of exponential functions in modeling radioactive decay, a process used for things like carbon dating ancient artifacts. The model is y of t equals y naught times e to the power of the quantity negative r times t, where y naught is the initial amount of the substance at time 0. The new term here is r, a positive constant called the decay rate, which measures how quickly the substance disappears. For the specific case of carbon-14, experiments show that the decay rate RAR is approximately 1.2 times 10 to the power of -4, assuming time is measured in years. Notice the negative sign in the exponent, which ensures the amount decreases over time, unlike the growth models we saw earlier. With this formula and the known decay rate, we can now answer the question of how much carbon-14 is left after a certain number of years. Now let us apply the radioactive decay formula to calculate how much carbon-14 is left after 866 years. Our first step is to evaluate the exponent, which is the product of the negative decay rate and time. We multiply -1.2 times 10 to the power of -4 by 866 years, which gives us an exponent of approximately -0.10392. Next, we raise the base e to this power to find the decay factor. The value of e to this exponent is about 0.901. This means the amount remaining is about 0.901 times the initial amount, which we call bi-naught. So after 866 years, about 90.1% of the original carbon-14 is still present, and a little less than 10% has decayed into nitrogen. Let us bring together the key concepts of exponential functions, which are essential for modeling any process involving repeated multiplications. We began with the general form, f of x equals a to the power of x, and established that the familiar rules of exponents apply to all real numbers, which is what gives these functions their smooth, continuous graphs. Out of all possible bases, we identified the natural exponential function, using the special number e, as the most important for calculus due to its unique properties. This function is the core of the model y of t equals y naught times e to the power of kt. This single, powerful equation allows us to describe both exponential growth when the constant coke is positive, like a financial investment, and exponential decay when coke is negative, as with a radioactive substance. The essential idea to remember is that this one family of functions can mathematically describe countless systems that change at a rate proportional to their current size. Let us take a moment to apply what we have learned about exponential functions, which is a great way to solidify your knowledge. I encourage you to pause the video and work through these two problems to test your understanding. The first problem is a direct application of the rules of exponents we just covered, asking you to simplify the expression, the quantity 9 to the power of 1/3, all raised to the power of 6, divided by 3 squared. The second problem uses our exponential model for a real-world scenario, where a bacterial culture starts with 500 cells and grows according to the formula P of t equals 500 times e to the power of 0.2t. Your task is to calculate the population after 5 hours and explain why the positive sign in the exponent, 0.2, ensures this is a growth model. This is a key distinction from the decay models we saw, which have a negative exponent. Working through these exercises is the best way to make these concepts your own.